Let's get the big picture again. There, this is what we're trying to do. Make a material, test a material. So we worked through and you watched me do the make material. And so now we're going to all start with that same data file and we're going to write the code that's going to allow us to perform a biaxial test. Okay. And then once we have that going, we're going to go back to make material and we're going to see if we can add those cement balls to that system and then test that. Play around with some of the properties and stuff, see what we've got. Okay, so let's go to make sure I'll do the same thing. So you should have created a directory here, cement chain making test work. And in there, you have a project called cement chain and you had that copied of the thing called make material.p2dat. Okay, so I'm going to fire up. You should fire it up too. Fire up that cement chain project. Okay. Oh, now I'm going to say, oh, I see. When I saved, I did that work and I created this in this project, but I didn't save the project. So I have to quickly rebuild that thing. So I'm going to say file, open, make material. I'm going to run it. I'm going to go to the plot. I'm going to rename it my view. I'm going to add the walls. And I'm going to say text value name. And let's stop for a minute right here. Notice we've got bottom left, right, and we've got a wall called platen. Let's talk about how that got created. And notice that that wall is bigger. So if you recall, we used the box command with the wall create, and that box gave us, bottom, left, right, and top, and they all were exactly this box shape. So what we need to do is we need to do that same thing, but then delete the top wall and build a new wall and give that new wall the name platen. Okay. So let's just look at make material because that's what's going on in here. So you can see on line 24, I'm going to return it because we want to look at it. So that just makes the box, right? So if we look at that, here we go, bottom, left, right, and top. And it all has the prefix MV because that's what we told it to use. So now I'm going to just do this wall delete which wall, range set name MV top. If I run that, it should have only 3 guys left. There we go. And now I'm just going to give it the vertices to make one new wall and they're going to overhang on the sides. So that's this guy. Notice the vertices are going from instead of minus 0.5 width to minus 0.6. But it's still 0.5 height for the Y. Okay, so when I do this, now I should have what I want. Bottom, left, right, and platen. Okay. Now I'm just going to run it. And you should get the same thing as me. I'm going to add the balls. Again, make them a little bit less thick outline. Make them yellow. Add the contact force chains, text value, force chain, scale by force directed, color, black, boom, redraw. There we go. Okay, so let's make a new data file, which is going to be called testmaterial.p2dat. First, I'm going to save my project to be safe. There, all that stuff is saved now. File, new data file, testmaterial.p2dat. Boom. Program return. Okay, so model restore. Remember in the previous thing we saved at the end, it called it the material. So that's what I want to restore. That's the guy that I'm going to do my test on. Model restore the material. Let's give a meaningful title. I'm going to say performing biaxial test. So I'm going to run this. Now, I don't see my title up here. So if you recall, you have to, for this view now, I need to check this guy, this checkbox, view settings. So just for that view, I can check job title, and then I can say OK. So that's putting my job title up here. And then I want to see the number of cycles up here. So I'm going to go into legend, and I'm going to check the box called step. And now it tells me mechanical step. All right, now, what do we got to all we really have to do now is give a negative y velocity to this thing. Okay, so let's just do that. Test material. But first, let's do this. The most important thing for this problem is going to be the velocity at which we move that platen down. Okay, we have to ensure that that velocity is slow enough that we actually have a quasi-static condition. If we make that velocity crazy high, it's going to be an overly high force. Just like if you did a test and you loaded the thing incredibly fast, then you're going to get dynamic effects. So we need to make the platen velocity slow enough that it's quasi-static. And one way to determine that is essentially choose a velocity, run the test, get a stress strain curve, set the velocity half as big, run it again, get a stress strain curve, and eventually you'll reach a slow enough velocity that you'll get the same stress strain curve all the time. If you keep going slower, it won't matter. You'll still get the same stress strain curve. And so that will then be the quasi-static velocity. And that's the value that you're going to want to use when you do your tests, because you want to basically load it as fast as possible, but not too fast. So let's just put in a number for now. Let's do 1e minus 2 meters per second. And I'll say platen velocity units meters per second. Okay. And now I just have to specify the y velocity. So that's wall initial velocity y, velocity dash y. And the value is going to be minus p-val. And I only want to do this for that wall that's called platen. So that's range set name platen. Now I'll put that in. And let's just run it. So I'm going to run it. I'm going to look at the view. And so I gave it a velocity, so I can just cycle 10,000. Boom. Hey, look, it's pushing down. And you can see the system responding, right? Now, let's just, for example, let's just monitor the displacement of that platen wall. And that should keep on getting bigger and bigger, right? So let's just do that. We'll just do this test here. Let's see if I can do this. Wall history, name. I'll call it platen disc. I don't know the syntax. Wall history name, platen disc. I think it's going to be displacement Y. And then I have to say the name of the wall. This is why you should never do stuff that you didn't actually do before. Let's see, F1, I'm trying to look up the wall history command. Displacement Y, and then this wall history block. Name, wall with name. So I should be able to say name. Displacement Y, the name of the wall is platen. Let's see if that worked. Created history, platen disc, Y displacement of wall 5. And because we're monitoring the displacement of the wall, remember that just keeps getting accumulated. Let's make sure that at the beginning here that the displacements are all initialized to 0. So wall initialized displacement, and that's a vector quantity. So 0, 0. So let's run this and hook in that history and make sure that the displacement is getting bigger and bigger. And the displacement should be a negative value. So let's see. So I'm going to run this thing. And let's go here. Let's just do cycle 1000. I'll run it 1000 steps. Now I'm going to add the history plot item. So I'll say plus and history chart, left-hand side towards the bottom, history chart. And now I'm going to say plus Y displacement right over here. Boom. And it looks like it worked. Turn off this other stuff. And so here we go. Flatten Y displacement. It starts off at this step number and it keeps getting more and more negative, right? Okay, we're going to need that in order to compute the strain in the Y, but we're going to need a fish function to get that. So let's see if we can do this thing. And we're also going to need a fish function to get the stress in the Y. So let's write the strain in the Y first, EPS Y. So go back to this. Just a second here. So we're going to need to say fish define EPS Y. And I'm going to put a comment. Positive is opening. We want this number to come out as a negative value of the, right? So epsilon Y, return. What is epsilon Y? It's going to be the following thing. What is this thing inside the return? Delta Y divided by height. Remember, height is already a fish variable. If you look over here, global symbols, because when we called the thing to make the material, we had a parameter called height. So, right, that's going to be a strain, delta Y over height. And now what's delta Y? So I can say local delta Y equals, there's a fish variable called wall.disp.y. Fish intrinsic, we call it. If I hit F1, wall.disp gets set the wall displacement. So, but now I have to give it a pointer to a wall. Which wall? Which wall? Which wall? So let's go and do this. I'm going to create a variable called wall pointer platen. So that means up here, I need to say global wall pointer platen equals, I want to get a pointer to the wall that has a name called platen. So there's a function called for that, wall find, and then I type in the name, platen. Boom. Return. Let me just see what happened there. Looks like it might have worked. If I look over here, WP platen is wall number 5, and it's a pointer. That's probably right. Okay. And so then I can use wall pointer platen to get the displacement in the Y of that guy. Okay. And the displacement's going to come out as negative. So that's what I want. If I just take that divided by the height, that's going to turn it into the strain. So see if we get this. What we're going to do is take a history of this epsilon Y. Okay, so let's run this. Cycle the 1000. So there's a history that we had from before of platen Y displacement, but now we want a history of the fish thing called epsilon Y. So let's just get another history chart. And now where is it? Why is it not there? Sorry. Oh, because I have to make a history of it. So here, I need to make a history of epsilon Y. So fish history, it's a fish history. I'm going to call this my epsilon y. And what you give it is then the fish function name, epsilon y. Fish history, my epsilon y. Now run it. Okay, now let's run it. Now when I come over here and in my history, look at it appears here. Oh, it's one of the histories. So I just say click this. And there we go. We didn't check the values, but we're going to assume it's right. Okay, here we go. My epsilon y, it's going negative as steps increase. So that's probably good. Now we're also going to want to write a function called sigma y to return the axial stress. So we'll do the same thing. We'll say fish define. The name of the function is going to be sig y. And again, I want to make sure I know what I'm going to say positive is tension. Okay, I'm using standard continuum mechanics conventions here. Positive strain is opening and positive stress is tension. And you're going to see that inside of that FIST package, you're going to be using, it uses those same conventions. Okay. So now we're going to return what? We're going to return something. What are we going to return? We're going to return the force on the wall divided by the area, the assumed area. So let's do this. I'll just call this wall force divided by wall area. So what's wall force? I'll create a local variable called wall force. I can get that. It's going to be a fish thing again. Wall dot force dot contact dot y. And then of course, which wall? Well, it's the one that we already have that thing, WP platen. So we're going to say WP platen. That's going to give us the force on the wall. And then the area of the wall. What's the area of the wall? What's the area that we want to use as the cross-sectional area for this system? What do we want to use for the area here to divide by? Area of the platen. It's the width multiplied by unit thickness. So we already have a variable for width. It's called width times 1. And I'm even, just to be clear, unit thickness. All right. And let's make a history of that. Stress times strain. Fish history name, let's call it my sigma y. What's the fish name? This fish function to call is sig y. And now let's run it. So now let's make another history. So what do I want to plot here? I want to plot sigma y versus epsilon y. So I click here, sigma y. There's sigma y. And then it says VS here. So the VS is the thing called my eps y. My eps y. Boom. Okay. And the sigma y is coming out as a positive number, even though it's compression. So let's adjust that. We want positive to be tension. So so this wall force, this is the total force pushing against the top wall. So that's coming out as positive. So we have to switch that. So let's where the return is, let's say minus wall force. Okay. We'll run this again. And now, what am I getting? I'm getting this axis is epsilon y. It's starting out over here and it's going negative. And as it's going negative, the sigma y is going more and more negative. So let's go and just reverse both of these things. So we have like the rock mechanics convention. and then we're going to have sigma y. So let's do this. So for the series sigma y, let's do, I think we want to do y reverse. There we go. And for this my epsilon y, click the reverse box. There we go. So let's put some names on this. So for the x-axis, axial strain, no dimensions. And for the y-axis, we're going to say axial stress, and that has units of pascals. And then let's make the x-axis start at 0. So the minimum of x-axis is going to be 0. Put in 0. Here we go. So axial strain. And let's say the y-axis also minimum of 0. Put 0 there. Come on. 0. And it's getting bigger. There was originally there was a compressive stress in the y direction from the beginning because this was a packed system. And now that stress is getting bigger as we continue on. Notice I'm going to put minus axial stress to be strictly correct. And this is minus axial strain. That's actually what we're plotting, right? So let's just run this thing. Let's get rid of this history of this platen displacement. We don't need that. We just had that at the beginning. Now we'll run it. Let's get rid of this history. Let's get rid of this history. There we go. Balls, contact forces, walls. Let's change that history to red so we can see it better. So I say series red. Redraw yourself. There we go, red. Now we just keep cycling because we already have that platen velocity. And so there we go. There's our axial stress strain curve getting generated as we run, right? So notice we created fish functions that were able to return to us the stress and the strain, and then we were able to make a history of those fish functions versus each other, okay? And here it's loading, and in this case, the sidewalls are not moving. So this is actually a uniaxial strain test, right? The material has nowhere to go. It's just going to keep on getting higher and higher compression in there. All right, we just did a biaxial test. All right, the last thing, let's see if we can make this work. So I'm going to save this project. No, this is a good thing to do too. Save it, quit, go back. Here's where I was. Here's the project. It just got saved at 9:51 a.m. Start it again. Make sure it still works. Looks like it's still working. Now, in order to do this, I first have to call make material, then I have to call test material. So what we will typically do is we'll make a new data file, and I'm going to call this, it's the master data file. So it's going to be called master.p2dat. And this data file is only going to do two things. It's going to say program call what data file, make material, and then program call test material. That's it. So run the disk, right? So it's making the material, it's making a save file, and then it's calling the next data file, which is going to do the test material. There we go. And now it's performing the test. All right. So now we're in pretty good business here. So let's save this. Okay. Now, okay, let's do the last step. We wrote that code that made those cement chains. So let's take a look at where that was. That was in a directory called cement chain elixir. Let's just make sure that works. I'm just going to fire up another PFC in this cement chain elixir. And let's just make sure that's what we think it is. If I run this, and there we go. And here I'm showing the groups and the contacts and okay, all these things. All right, looks like that worked. So let's shut that down. Now, make and test, work, that's where we are. Okay, let's go, and for that Elixir thing, let's copy that data file, and we're just gonna change a couple things. So pull that into our working directory. And let's just rename this, let's call it Fred for now, because we're not gonna actually, we're just gonna suck it in and just take a portion out of it. So I'm gonna say file open Fred. Now, all that we want to do is have this fish function, make cement balls. Everything else in here was just like, building a test model and stuff. So what I'm going to do here is I'm going to copy that make cement balls. And in my make material now, before I'll say the material, and I'll call it no cement. Then define this function, make cement balls. Call the function. Let's see if this works. And what size are these balls? These balls are sizes of like 0.05. So let's make the cement balls 0.01 for now. 0.0. Let's make 0.02. Okay. And then let's save that as, call it the material, and we'll say dash cement. Okay. Let's run it and see what happens. So it's making the material. It hasn't yet called that function because we need a packing, and then it's going to go through there. Now watch what's going to happen. Oh, let's see. Oh, look, it threw an error. Balls at contact do not have same radius. Oh yeah, we were careful when we wrote this function, and that's something we assume has to be the case. Otherwise, this isn't going to make sense. So if our function is pretty stupid. So when we generate these balls, we're going to have to give our min and our max all the same. So let's make our min and our max all the same and run it again. Now our function should be able to work. Let's see if it works. No idea. Look at it, it's creating all sorts of balls. And somehow it didn't like this. Ah, yeah, okay. Let's just look at what we got. Ball. But let's do the group. Hex to val, let's get all this other stuff out of the way. Ball, hex value group. Now we're getting some interesting stuff. We got color, default, cement, gray, none, yellow. Right. Not sure. Yeah. And those cement balls, okay. Doesn't quite look what we want. Notice we created vols here. Well, okay, hold on. Let's just leave that for now. Okay. Let's make these things. Oh no, that's probably okay. Let's make these, let's see. Here's what it's saying. Unable to convert parameter type from pointer to facet to ball pointer. The heck does that mean? Notice what we did here. It says we're visiting all the active contacts, but actually we don't want to put cement. We only want to put cement in if it's a contact between two balls. Okay. And so what we have to do is we have to put a check in here, and we basically have to say only continue doing this if this contact is between two balls, not between a ball and a wall. And it's going to take me a little bit to figure out how to do that. We're going to have to make a call to check that. There's going to be a way to check that. But we've reached the end of our time here. And so we'll spend like 10 minutes reviewing this and showing how to do that. And hopefully then we'll have all our cement on there. And we can play with that a little bit to see how it behaves.